In this video, we continue with finding the limit of trigonometric functions. So this is the third case. We already did the first case. We saw some important properties about sine, cosine, tangent. We did some examples there. So it is important to watch the first case of finding the limit of trigonometric functions before continuing with the third case. You can click on this card which will appear here to watch it. If you watched the first case, we had also the second case of finding the limit of trigonometric functions. If you didn't watch it also, you can click on this card which will appear here to watch it. If you watched both of them, so welcome to continue, you can continue with the third case, okay? So when solving limits involving trigonometric functions like sine squared x or cosine squared x, if direct substitution leads to an indeterminate form, such as 0 divided by 0, you can simplify the expression using the Pythagorean identity. Sine squared x plus cosine squared x is equal to 1. Okay, so this is a Pythagorean identity. So this identity helps to simplify and solve the limit by transforming the trigonometric functions into a more manageable form. Let's see first example. So find the limit as x approaches to 0 for 1 minus cosine x over sine squared x. So keep it in mind, we already said also that constant numbers, we don't touch them, 1 remains 1, okay? Then cosine of 0 is 1, sine square of 0 is 0. So this leads to indeterminate quantity, 0 divided by 0, right? So what we'll do is we'll take advantage from the Pythagorean identity. Pythagorean identity says sine squared x plus cosine squared x is equal to 1, okay? So what we will do is we'll take cosine squared x to the other side, and we'll get sine squared x is equal to 1 minus cosine squared x. So now we'll take advantage from what we did here by saying, so we'll rewrite our equation, and instead of writing sine squared x, we will write 1 minus cosine squared x. Why? Because here we proved that sine squared x is equal to 1 minus cosine squared x. So writing instead of sine squared x, 1 minus cosine squared x, this does not change the value of the equation, okay? This will help us to find the limit, okay? So then we already saw that a squared minus b squared, this is difference of squares. We already explained that also. You can click on this card here to watch the famous identities. I will quickly make a reminder for you. So a squared minus b squared is equal to a minus b multiplied by a plus b, okay? So this shape 1 minus cosine squared x is the same as this one. Here, if I tell you 1 square is equal to 1, okay? So 1 here, you can say it is square by default. So it has this one and this one has the same shape, so you can apply the difference of squares. So what we'll do is, so instead of writing 1 minus cosine square x, we will write 1 minus cosine multiplied by 1 plus cosine. So we will apply this identity, this one here, this formula, okay? Then this one will disappear with this one, okay? And we'll get 1. So 1 minus cosine x divided by 1 minus cosine x is equal to 1 here. So we'll get 1 over 1 plus cosine of x. So now find the limit as x approaches to 0 for 1 over 1 plus cosine x. So if you substitute x by 0, so you'll get 1 over 1 plus 1, and this is equal to 1 over 2. Let's see second example. So find the limit as x approaches to p over 2 for 4 cosine squared x over 1 minus sine x. If we substitute each x by p over 2, so constant number 4 remains the same, okay? Then, and 1 also remains the same. Then cosine square of p over 2, so cosine of p over 2, so p over 2 is 0. so it is 0 here. Then sine of p over 2 is 1, so we have 1 here. Finally, this leads to the division 0 divided by 0, and this is indeterminate quantity, we have to avoid it, right? So we'll take the advantage from the Pythagorean identity. What we'll do is in this time we'll take sine square x to the other side, and we will get cosine square x is equal to 1 minus sine square x. Okay, so instead we will rewrite our equation. So instead of writing cosine square x, here we proved that cosine square x is equal to 1 minus sine square x, right? So we write 4 multiplied by 1 minus sine square x, okay, instead of cosine square x, over 1 minus sine x. Now what we will do is we will do the same. We will apply this identity, the difference of squares, a minus b squared, okay? So we will get 4 multiplied by 1 minus sine x multiplied by 1 plus sine x over 1 minus sine x. So this will disappear with this, okay? 1 minus sine x over 1 minus sine x, and we will have what will remain is 4 multiplied by 1 plus sine x. So find the limit as x approaches to p over 2 for 4 multiplied by 1 plus sine x. So we'll substitute x by p over 2, and we'll get 4 multiplied by 1 plus 1. This is equal to 8. Okay, so the limit as x approaches to p over 2 for this equation is equal to 8. Okay. Let's see third example. So find the limit as x approaches to p over 6 for this equation. So as we said before, constant numbers 2, 1, 4, 3, 2, 1, 4, 3, we don't touch them. And then we take the sine, so we substitute each x by p over 6. Sine of p over 6 is 1 over 2, so 1 over 2. And cosine p over 6 is the square root of 3 over 2, and this square remains here, okay? So this leads to indeterminate quantity 0 divided by 0. What we will do is we'll take advantage from Pythagorean identity. We will take sine square x to the other side, so you'll get cosine square x is equal to 1 minus sine square x. Then we will substitute cosine square x by 1 minus square 1 minus sine square x, which we proved here. We proved here that cosine square x, this one, is equal to 1 minus sine square x. So we can do it here. We can substitute cosine square x by 1 minus sine square x. Then we will multiply 4 by 1 and 4 by sine square x. We will get 4 minus 4 sine square x and 3, and this the numerator we didn't touch it, okay? Then 4 minus 3, okay, this will be equal to 1, so you get 1 minus 4 sine square x. So this is difference of squares, as we said before. We said this is like a square minus b square, which is equal to a minus b multiplied by a plus b, okay? So this is the same, so you will get 1 minus 2 sine x multiplied by 1 plus 2 sine x. So what we will do here now is, so here you see we have 2 sine x minus 1, but here we have 1 minus 2 sine x. So what we need to change is we have to get here 1 minus 2 sine x instead of 2 sine x minus 1. Why? Because we need to get 1 minus 2 sine x in order to say this will disappear with this, right? We have to do the division to get rid from both of them. So what we'll do is we'll take minus, we'll do it as follows. So we'll take minus out, and we'll say 1 minus 2 sine x. So if you multiply sine by 1, so you'll get minus 1, and sine multiplied by minus, we'll get plus 2 sine x. So this means we didn't change anything. You see, again here we have negative 1, positive 2 sine x, positive 2 sine x. Okay, so what we do here, you see we have minus 1 over 1 plus 2 sine x. So what we did here, we said minus multiplied by 1 minus sine x. So this will disappear with this, okay? And we still have minus here, minus 1, okay? Then we find the limit. So find the limit as x approaches to p over 6 for this equation, minus 1 over 1 plus 2 sine x. So we substitute x by p over 6, we'll get 1 over 2. So finally, we get the limit is minus 1 over 2, okay? Thank you for watching, and hope to see you in the next video.